Okay, Coroneos 100 integrals number 44. So have a look at this question here. We need to integrate dx over x squared plus 1 times by x squared plus 4. Now this question is a bit tricky to do. We need to use partial fraction to do it, of course, right? Because as you can see, the denominator consists of two quadratic factors. So we need to decompose this one into partial fractions, and then we need to use the method of substitution to work out the ax plus b, cx plus d. So let's start with this process here. All right. So first step, we need to change this one. How about we just write let 1 over x squared plus 1, x squared plus 2, so x squared plus 4 equals to ax plus b over, now remember it has to be ax plus b for the numerator since the denominator is a quadratic, and then cx plus d x squared plus 4. Alright, so once we have finished that, we need to cross multiply, and we need to make sure that we're equating the cross multiply, the product equals to 1 here. Okay, so make them equal to each other. So we end up with ax plus b multiplied by x squared plus 4 plus cx plus d, and you multiply by x squared plus 1 equals to 1. Okay, now if we start to use the normal method to substitute, like by substituting x equal to 0, by substituting x equals to 1, x equal to minus 1, x equal to 2, and it keeps going, we're going to end up with a lot of different equations, right? And we need to solve it individually. Okay, so we probably need to solve it maybe using simultaneous equation. It's going to take a long time to do this question here, so we need to use probably the easiest way to do this question is we're using complex numbers to help us to solve it. Okay, reason for that is because as you can see, we've got x squared and x squared here. So if we use a complex number substitution, it's just making our life much easier to do this question. Okay, so what we can do here is we can actually let x equals to I, because by letting x equals to I, we can eliminate this part or this expression here. All right, because I squared is equal to minus 1, and minus 1 plus 1 is equal to 0. So this entire term disappeared, and we end up with only one equation with ab in it. And because it's a complex equation, so therefore we can equating the real part and imaginary part. Okay, let's just have a look at what's happening. So if we substitute x equals to I, we get a times by I plus b, and that becomes negative 1 plus 4 is equal to 1. Alright, and then if we move this one over to this side here, it becomes 1/3. So we've got ai plus b is equal to 1 over 3. Now, if we just equating the real and imaginary part, okay, if we're just equating the real and imaginary parts, as you can see here, there is no real imaginary parts, so therefore that's just equal to 0, and then the real part is just equals to 1/3. All right, so therefore at the end, we end up with a equals to 0, b is equal to 1 over 3. So this is much easier to do by actually letting x equals to a complex number. All right, so once we finish that, we can actually now move on to the second part, which is this part. We want to get rid of this. By trying to get rid of this part here, we need to make sure this factor is equal to 0. So if we substitute x equals to 2i, we can cancel the 4. All right, so if we substitute x equals to 2i, then the first term disappeared. Because 2i squared is equal to minus 4. So we end up with c times by 2i, so 2ci plus d, and then minus 4 plus 1 is equal to 1. Alright, and if we simplify that, we get 2ci plus d is equal to minus 1 over 3. Again, we can equating a real part and imaginary part. We end up with, okay, let's have a look. The real part, d is equal to negative 1 over 3. And c is just equals to 0, okay? So therefore we get c equals to 0, d equals to negative 1/3 by equating the real and imaginary part. Alright, so therefore, hence, we end up with this expression here. Let me just copy this one down first. So now, since we have everything we need, we can rewrite this, fraction instead of ax plus b and cx plus d, we end up with, we know that it's just equal to 1/3 here for the first fraction, and for the second fraction is negative 1/3. Okay, and now we can integrate this much easier comparing to the previous one. So therefore, when we're integrating the original equation, the x squared plus 1, x squared plus 4, okay, is it now equals to 1/3 integrate 1 over x squared plus 1, all right, minus dx. Okay, we can also separate that into two separate integrals, 1 over x squared plus 4 dx. Now this just becomes an example of inverse trig integration. So that becomes 1/3 tangent inverse x. That first one is really easy. Now the second one, because we have a 4 here, so we do need to change that 4 in terms of 2 square. So that gives you 1/2 tangent inverse x over 2. And that's just the formula for the inverse tangent. Alright, so for those of you that still have issues with this one, what I did here is just change the 4 to 2 square, and then applying the formula that gives us 1/2 half tangent inverse x over 2. Alright, plus c. That is the reason. Alright, so finally the answer is 1/3 tangent inverse x minus 1/6 tangent inverse x over 2 plus c. Okay, and that's how you actually do this question, by using a complex number substitution to speed up the process. Otherwise, if you're using the real number substitution, you'll end up with maybe 4 equations, and then you're going to solve it simultaneously. Okay, thanks for watching.